I'm from Machine Zone. Machine Zone is doing several wonderful things with real-time, and one of the technical underpinnings is a WebSocket-based real-time messaging protocol. So to remind you, the WebSocket is a persistent layer on top of TCP, which is initiated by doing an HTTP request with some special headers, and the response indicates whether all of the systems between the client and the server support the WebSocket. If the response goes through all right, then the bidirectional connection is established, and then two systems can exchange messages in both directions simultaneously with very little overhead, and with a number of features that can be added on top, including custom application-specific features like some additional compression protocols and support for many application-specific stuffs. The small caveat is that not all proxies have been upgraded in the world, so the secure WebSockets have a better chance to penetrate all of the firewalls. So for some of you who never tried WebSockets, if you're trying to deploy an application, it's better to start with WebSockets, which is essentially like HTTPS, something over SSL layer. Machine Zone, a couple of words. The flagship products are two games, which are very successful. They're very dynamic and real-time in terms of having a very short time between the user action and the feedback, which may result in a change of game design elements and suggestion of different things to purchase. And this real-time feedback, or shortening the real-time feedback, has enabled us to reach the first places in Apple Store by revenue. So we are heavily invested in real-time. We know the dollar value of every millisecond shaved, and therefore we need to be competitive in this space. And we think that this real-time efficiency is a competitive asset. The real-time here is something that works across the internet scale of timing, meaning milliseconds or dozens of milliseconds, not necessarily the hard versus soft real-time distinctions that were introduced by embedded systems engineers, and not something that we necessarily have to adhere to. The challenges that we have developing the significant scale system or large scale systems is, first of all, we have to support hundreds of millions of global users and send millions, or actually hundreds of millions events to them for different things, for click streams, for user-to-user messages, for chats, for translations. And if we are talking about WebSockets, the existing TCP level load testing tools do not work well with WebSockets because you need to do this HTTP-based handshake first, so you cannot really get the standard TCP testing tool and try to use it against the WebSocket API. Because of that, we developed a couple of benchmarking / load generator tools, which are TCP Kali, a command line utility for an individual developer, and MZBench, which is a distributed server-based thing. It can be used on a single computer, but typically you would install it somewhere, such as on AWS, and you would drive a number of, any number actually, of individual testing nodes and drive the traffic from all of those dozens or hundreds of nodes into the specified destination. The MZBench was described in that particular talk by Epiphan. I'll share the presentation. You will be able to watch it if you want. But this presentation is about TCP Kali. TCP Kali supports very large-scale persistence on a single box. Whatever persistence has in persistent connections and multiple simultaneous connections. The large scale on a single box would mean that we can quickly open millions of connections from a single box or terminate millions of connections on a single box. It is a little bit non-trivial things, and I will describe how TCP Kali helps to develop those kind of large-scale systems. TCP Kali has to be extremely fast in order not to introduce additional latency and in order not to interfere with the operation of the software that it's trying to test. The main way we are using it is we set up software on the local host and we drive the traffic for local host. This is for development purposes. And then for many additional benchmark, we do the proper setup where we would drive traffic from other machines to verify our findings. And typically you would have wildly different problems, and you will see wildly different performance. But local host testing is still useful to figure out the profile information, for example, and your bottlenecks in the code, whether the bottleneck is in parsing or application-specific code. TCP Kali tries to be developer-friendly. It's open source, and if you have Mac, you can quickly install it using brew install TCP Kali right now. When we develop large-scale systems, we have several categories of challenges, and we need to solve them with appropriate tooling. The stress testing as an activity, as something that you do if you do that, tends to break things. It destroys your systems if they were not tested before. So if you haven't tested your software using stress test tools, you're in for a surprise if you do it the first time. It will break. Many clients, as in multiple clients, hundreds or thousands or hundreds of millions of clients accessing your system simultaneously, will break things. Slow clients, which do not consume information as fast as you're trying to send to them, will break things in your software. Some WebSocket shenanigans like framing options, combinations of different frames, ordering of frames, and incomplete frames will break things. So this is a borderline security thing that you can do with TCP Kali, though TCP Kali was not designed for security specifically. And while you are doing development and testing, you need detailed visibility into what's going on, meaning that you have to be able to drive the tool in a way to discover the failure and maybe try to get some information out of it to help you to debug. So I will describe how to use TCP Kali to address all of those categories of problems. The first is stress testing. The genius idea is to repeat message many times as fast as possible. The first line here suggests that we are using WebSockets to connect to the specified IP address and port, and we are repeating my data in separate WebSocket frames over and over. If we do not specify WebSockets, TCP Kali can be used as a straight vanilla TCP load testing tool. Here we are using -d, which means dump. The dump allows you to discover what we are actually sending, what we are writing into the socket, and what is getting received from the socket in a formatted way. In this case, we are combining them, and actually it doesn't make sense to ask TCP Kali to drive a lot of traffic and dump it to the screen if we are not specifying a rate, because the default rate is as fast as possible, and your screen will be filled with some my data things. I will show everything to you how it works. And TCP Kali can work as in a server mode and in a client mode, and the last line shows how to test itself. So it opens this listening socket, it opens the active socket, connects them together, and tries to send as much traffic as possible, consisting of Z's. -m means message. As promised in the description of this talk, I will show you how to break Node.js. This is the description of what I'm going to do. I'll grab the code from a random article describing how to set up a simple WebSocket server using Node.js. And I will run this server, and I will drive some traffic into that, and we will see what happens. it will take maybe a couple of minutes to demonstrate that. It's not that long. So here we see how system behaves. Here I will open up the node. Everyone sees that? OK, so what we have is a short Node.js script which just echoes whatever it gets using WebSockets. The node version is 6.4.0. I'm running it up, and it listens, apparently. And then I'm driving some traffic to it. So I'm sending these individual Z characters, each one in its own WebSocket frame, to the server. Am I doing it in the right? OK. OK, so what you see is that how TCP Kali sends messages into the Node.js script. And then I'll show what it actually sends. It sends frames with specific WebSocket masking, and the script, the Node.js script, responds with these back. So let's do something a little bit more challenging. We would not print anything on the screen in the Node.js script, and then we would do the same. So we are still sending. We are receiving something, but we are not printing on the screen. Now, we are removing -d, and we are removing the speed specification, so it will try to go as fast as possible. What you see over here in the top is amount of memory used by Node. So it will crash. Hopefully, it will not crash my computer. But the reason it will not crash my computer because TCP Kali stops after 10 seconds by default. So you can specify -t 1 hour, for example. Then it might actually crash my computer. But I will not do that. But you can see how easily it generates like 500 megabits per second, and it goes down. The node memory utilization goes up, and you see how it will crash the node eventually. So go back to the presentation. It's pretty much a fundamental problem with Node.js. So I could have done something with this WebSocket, but I couldn't have solved this problem. So now, many clients. The idea is to be able to establish millions of connections to the same IP address or multiple IP addresses. So you can actually specify multiple IP addresses and ports, and it will round robin the connections between them. So here I can specify 1 million as the number of connections. You cannot originate more than about 60K connections from a single host. In order to support more than that, TCP Kali actually grabs all of the aliases, interface aliases from that machine, and uses them all, and uses them as the list of source IPs. So it actually is able to produce more than 1 million messages, 1 million connections. In this particular case, we are saying that the message rate is going to be mostly idle. We are sending a message every 10 seconds. And the message is a specific WebSocket specific ping message. And we are going to do this test for 1 hour. This is the same thing, but using the short options. So this is how you typically write it in the scripts. So it can be understood by the readers. And this is how you typically work yourself in the command line. And the I've tried it with multiple millions, like 6 millions on a single host. The problem is that Amazon allows you 8 aliases, and if I do it in my lab, I can use hundreds and hundreds of aliases if I have large enough IP space. I did that for millions, it works. It eventually hits many, many limitations in the kernel, but the stock Linux kernel can do a few millions if you do a couple of sysctls right. And let me show you how TCP Kali handles millions of connections. Handles as in suggest things to modify. So let me walk you through. I've tried to create 1 million connections to the local host. And it says that the open files limit is too low. It suggests changing the file max syscontrol. The open file limit, as in ulimit, is too low as well. And you can use ulimit -n. Then there is local port range, which is a limitation. Then the time wait probably will hit you. Then the IP filter, which is most non-trivial thing, is something that will prevent you going higher than about 60K. Or it will be very slow if you go above that. So those things, if you address them and change all of those things one by one, it will allow you to create those many connections. Typically, tools don't do that, so people assume that it's kind of either very hard or impossible. But if you do those things, it will trivially work. By the way, a little experiment I can do here is a demonstration of how TCP Kali works with itself. So right now, it is doing 23 gigabits per second on a single core inside a VM. So if I do 2 connections, because my air has 2 cores, it will do some different number. Okay. Okay, so depending how it's got scheduled among cores, you can see up to twice as much bandwidth. So here we see about 40 gigabits per second on 2 cores. So let's go back to the presentation. Next problem, slow clients. Slow clients are clients which do not consume data as fast as you send to them. So if your application is written incorrectly, it will buffer data in all sorts of buffers. The first buffer limit it will hit is the TCP sending buffer, which is somewhere between several dozen kilobytes and several hundred kilobytes. And then you will start hitting the application level buffers if you have them. If you have written them incorrectly, you will probably hit some errors. If you haven't written some kind of DOS protection, then eventually your memory will be exhausted, especially if you're trying that with millions of clients, and your application will crash. You can specify bandwidth limit for downstream and for upstream. It's symmetrical. And this way you can try out with slow clients. I've read some Google research that tried different open source tools and servers and applications specifically against slow clients. And it turns out that slow clients pretty much break the absolute majority of the open source servers. So it is very important to try your application with slow clients. Now, the next problem is WebSocket framing. The WebSocket framing is peculiar. You can send pretty much arbitrary amount of data inside a single socket frame. So to support testing that, TCPKali supports including files, and those angle brackets are verbatim. You actually type them in. And then you send a binary frame. Here you send a binary frame which contains all of this file. And obviously you can send something like a several gigabytes file to the server and see how it copes. Then the other peculiar thing about WebSocket is that it has text and binary frames, but then those frames can be incomplete, and then those frames are followed up with continuation frames. So what you can try is you can create an incomplete frame, then multiple incomplete continuations, and see how the server side reassembles them. We actually hit a couple of interesting problems when we first tried to do that, because we thought that we had protection from that, but it turns out that we didn't have good enough protection. Even though we had protection, there was no way to test, so TCPKali allowed us to test and find problems in with memory utilization. Then the next one. The next problem is developer visibility. We have different types of dumps. We can dump all of the data which comes into all connections, comes out of those connections, dump data which comes into any random single connection and goes out of that. And minus D is LAS to minus dump 1. Something that I will probably not be able to describe is latency-related options, which allow you to use histograms. Internally, it uses histograms to figure out 99th percentile and 99.5, and pretty much you can specify it in the command line what kind of percentile latencies you need. And it computes them, and it shows you those percentile latencies, and this way you can check whether your code is consistent with your SLA, for example. And statsd, finally, is something that allows long-term storage and preservation of TCPKali experience. Essentially, if you are doing an hour-long test, all of those parameters, input, outputs, and latencies and whatnot, gets exported into statsd, which is typically a local daemon. And then if you use something like a Datadog, you can see it on the graphs, and you might see very interesting things like the periodic behavior, like every 10 minutes it goes down, then it goes up, and then you can do something about it. So it's not something, TCPKali is not only a tool which can give you an aggregate statistics, it can actually gives you that statistics as it goes every several times a second using command line and statsd export. So I had this slide just in case. Here is an example of the full WebSocket communication. So we say that we will be sending Z characters to this IP address for 1/10 of a second. And first it creates a GET request, waits for the HTTP response, and then starts sending those Zs. And since we are short-circuiting it to itself, it doesn't reply anything, so we're just sending them. So it shows how it highlights what is getting sent and how many bytes we are writing to the kernel, to the socket, and what we are actually receiving from the kernel. And then it reports something like bandwidth per single channel, aggregate bandwidth, packet rate estimates, total amount of data sent, test duration, and so on and so forth. There are several additional options available when you enable latency measurements. And there is also several levels of verbosity that you can add in order to show more. TCPKali is not a security testing tool. I heard that burp suit is very good. We have a special security team that uses a multitude of tools to test our security, but TCP Kali is not one of them. The distributed testing can be done with multiple TCP Kalis, but MZBench is much better and UI is much better for distributed testing. It aggregates everything and presents using web UI. TCP Kali is a command line utility. Scenario-based testing is obviously not supported because the goal for TCP Kali is to be extremely fast. And you can simulate a little bit of variety in your messages, but by using regular expressions as generators of random data. Source is available, documentation is available. I'm done. Questions?
So the request can be as complicated as a database query?
I didn't get that. Could you repeat, please?
Like a database query wrapped in, framed in a request and then sent to the server. Can that?
Yes. So when you are, I can actually show you. We have a minute. What you are doing is you can specify your message, and your message can be whatever. If it's text, for example, a JSON message, you can send that JSON message, and it will be encoded in a frame. If you need to do something prior to sending this message repeatedly, you can do something like -1. And then this message will be sent once, and then multiple messages of this kind will be sent. And obviously, you can use a database query there. You can insert it there. You can do something like http get/full-bar http 1.1 rn to simulate HTTP. So it will work, and it's explicitly supported. And then, for example, let's try it with google.com. Do I have internet? Probably I do. What? -D. OK, so here we see that we've requested a foo.bar, and Google replied with some content. So you can use that to access databases which are not specifically, which do not have very non-standard authentication or that are only available through SSL. TCP Kali doesn't support SSL right now.
So MZBench is that publicly available?
MZBench is also open source, and it's also publicly available.
Okay. Oh, so it's open source, but it's not based on TCP Kali?
No, those tools have been written pretty much simultaneously and are getting evolved simultaneously in slightly different directions. And both tools are heavily used in MZ to develop RTplatform. That's it. Thank you.